Good night, we're Miguel Mejia and Angel Garcia, and today we're going to present the final presentation of our project, Mobile Robot for Selective Tomato Harvesting. A mobile robot for selective tomato harvesting using RGB division is what we're going to be talking about right now. And over the next presentation, we're going to work through the problem, the proposed solution we found, our system design, the kinematic model we built, and the validations we conducted, the results from our reference literature, and the ROS execution we executed. Harvesting robots have at least four problems to solve each time they go into action. First, we have variable lighting. Normally, in a trial environment, we'll have control lighting and control variables. When they go out into an open field, this goes out of control, and sometimes this is a hard variable to predict and control. Next, we have occlusion. Leaves and stems hide part of the fruit, breaking simple detection heuristics and also causing collisions or obstacles in a way that we do not perceive or we do not anticipate for. Then we have irregular geometry. No two plants share the same shape. The arm must reach a certain position and a pose it has never seen before, so it can cut the fruit accordingly. And then we have delicate cutting. The wrong orientation on the peduncle either misses the cut or may damage the fruit. That's why we need to not only predict the center of the fruit, but also its pose so we can reach an accordingly correct cutting pose. For our system design and architecture, our robot, called Robot Cosecha, pairs a differential base with a 6-degree of freedom arm, a 9-hand RGBD camera, a 2D LiDAR sensor, and a fixed cutting tool. Nav2 handles raw navigation with Move It, plants the arm, directly keeping separate so we never treat the non-holonomic base as if it were just another joint. This means we treat it as two separate systems, so if Move It plans a trajectory that maybe the differential drive base couldn't comprehend or couldn't fulfill, then we won't have that issue since we're treating it as two different controlled and planned systems. And on the right, you can see the greenhouse whirling gazebo and the arm operating inside the crop row in Narvis. There we can see how the arm performs inside the controlled environment and inside our simulation. Now, if we talk about our kinematics, the kinematic chain runs from the work frame through the moving base. A fixed offset and a 6 Denali Hardenberg links to the endpoint. We didn't stop at writing the forward kinematics equation. We built a full 6x8 spatial Jacobian, which falls in both base velocities and all 6 joint velocities. And we validated it two ways, against a finite difference approximation, as you can see in the slides, with an error of 3.2 times 10 to the minus 8, and through a singular value analysis at the transport configuration, given a condition number of 5.78 and full rank of 6, confirming we're far from a singularity and we're still operating within the range of safe operations. Here you can see how we obtain both the Jacobian and the Denavit-Hartenberg kinematics and the conventions we made. Since with this and the validations we conducted, we can be absolutely sure we are fulfilling the kinematic goals we fixed for our robot. Now, if we talk about inverse kinematics, solving forward kinematics was not enough. The robot needs to go from a detected cutting pose back to joint angles. We need to go the whole way from pose to angles and to joints, and from joints back to angles back to pose. We implemented three approaches. The classical decoupled geometric solution failed on all 20 test poses. We traced this to the elbow offset in link 3, and we documented it openly as a debugging item rather than hiding it. We didn't fully validate this part, so it is held up still for validation and still to be set up limits and a safe frame where we can test it. And then we also have both numerical processes using damped least squares and converge 100% of the time. One solving just the arm, the other coordinating both the whole body and the base included.